hoping to make this the shortest video in my history of filmmaking. So let's get going. Formal charges seems like a misnomer because it's not really formally a charge, even less so than oxidation state. Some kind of positive and negative tool that we use for deciding what Lewis structure is more favorable. If you remember, to draw Lewis structures in the first place, we count the number of valence electrons each atom brings into the mix, molecule or polyatomic ion or something, and adding all those up, try to decide how the bonding looks. We'll do a similar thing here, except after we have the bonding in place, we count down from that initial number of valence electrons. We count down one electron for every shared pair and one electron for each electron in a lone pair, which makes no sense until we try it. By the way, we try to keep the formal charge as close to zero for each atom as possible. If we have a bonding structure or bonding scheme that causes a formal charge to be too far from zero, that's not favored. Even -1, +1 might not be favored. In any case, here's the resonance structure, non-resonance, Lewis structure for this sulfite ion, 2-. Sulfur brought in 6, and so did oxygen, brought in 6 valence electrons to this mix. If you think back to our pattern of valence electrons, so 6, 5, 4, 3, 2, 1, 0. Try to watch carefully to my pointer. Again, that's 6, 5, 4, 3, 2, 1, 0, 0. 6, 5, 4, 3, 2, 1, 0, 0. 6, 5, 4, 3, 2, 1, 0, -1. Formal charge -1. Same for here. So -1 and -1 add up to -2. The formal charges sum together to give the charge on the ion if it is an ion, or if it's a neutral molecule, the formal charges must sum to be 0. Oxygen brings in 6, 5, 4, 3, 2, 1, 0, 0. Hydrogen brings in 1, counting down from 1, 0. Same story here. Carbon brings in 4, 3, 2, 1, 0. Interesting, formal charge 0. So 0 formal charges are preferred and stable. Let's see, or we could do something like this. Carbon brings in 4 valence electrons to this, is it formaldehyde? I think it is. 4, 3, 2, 1, 0. 4, 3, 2, 1, 0. 4, 3, 2, 1, 0. 6, 5, 4, 3, 2, 1, 0. Interesting. Confusing. 4, 3, 2, 1, 0. 6, 5, 4, 3, 2, 1, 0. 6, 5, 4, 3, 2, 1, 0. -1. 1, 0. 0 formal charges, -1 formal charge, -1 ion overall. 6, 4, 3, 2, 1, 0. What? Did I make a mistake? No, my bad. Duh, I did. Nitrogen brings in 5 valence electrons. 5, 4, 3, 2, 1, 0. 4, 3, 2, 1, 0, -1. -1, -1, -1, 0. So far, we're still confused as to why are we doing this. Oh, here we go. Here's an example. If I had carbon disulfide and drawing the structure like this, you could say 6, 5, 4, 3, 2, 1, 0. 6, 5, 4, 3, 2, 1, 0. 4, 3, 2, 1, 0. This structure has 0 formal charges all straight away across. But if I imagined why would it do it this way, you could imagine it happening. 6, 5, 4, 3, 2, 1, 1. 6, 5, 4, 3, 2, 1, 0, -1, -1. 4, 3, 2, 1, 0. This one, because it goes to +1 and -1, just even that little bit further away from 0, kind of hints to us that this one's not so favored, but this one with the 0 formal charges is favored. Excuse me. Let's try this one. Can I make this larger? I can. What do you know? Cool. You already know answer, but let's try it again. Let's try it already anyway. 6, 5, 4, 3, 2, 1, 0. 5, 4, 3, 2, 1 plus 1. 5, 4, 3, 2, 1, 0, negative 1, negative 1. Formal charges are in green, of course. 5, 4, 3, 2, 1, positive 1. 5, 4, 3, 2, 1, 0. 0 formal charge. 6, 5, 4, 3, 2, 1, 0, negative 1, negative 1. Interesting. Negative 1 and positive 1 make 0. 5, 4, 3, 2, 1, 0, negative 1, negative 2. Oh my goodness. 5, 4, 3, 2, 1, 5, 4, 4, 3, 2, 1. Yeah, positive 1. 6, 5, 4, 3, 2, 1. Positive 1. Positive 1, negative 2 makes 0 overall, but this is not favored because the negative 2 formal charge is way too far away from 0, and these are far away from 0 as well. It seems like there might be no preference between this one with a 0 plus 1 minus 1 and this one with a 0 plus 1 minus 1, but actually the more electronegative atom is probably more likely to get the negative 1 or the negative formal charge. So I'm going to say this one is more favored because oxygen, being more electronegative, gets a negative 1 charge, whereas one of the nitrogens is plus 1, one of them is 0, better than having oxygen 0 and this nitrogen negative 1. Nitrogen is not as electronegative as oxygen. But I bet in a sample of billions and billions and countless trillions of these molecules, some of them might be in this state because the formal charge is still 0. I should say not too far from 0, but just as it is with this one. But I would still claim that this billions and billions of molecules of this would probably be in mostly this state with some measure of a triple bond here and some measure of a single bond there. Alright. Oh, yeah. Oh, let me zoom it out a little bit more here. Which one of these is favored? I think I'd have to, now I'm not mentioning the resonance structures here, or, wait a minute, as a matter of fact, I think 1 and 3 are resonance structures of each other. So there might be no preference between 1 and 3, or they're identical, i.e. But certainly Roman numeral 2 and Roman numeral 4. Oh, excuse me, is it nap time or what? This is in the afternoon. This is my post-lunch lethargy. Alright, let's count them up. Let's determine the oxidation states. No, bzz, the formal charges. Hello. Different video. Alright, 6, 5, 4, 3, 2, 1, 0, negative 1. 6, 5, 4, 3, 2, 1, 0. 6, 5, 4, 3, 2, 1, 1. Formal charges. That looks like, oh yeah, structures of 1 and 3 are resonance structures, so they both have the same formal charges going on. Roman numeral 2 had 6, 5, 4, 3, 2, 1, 0, negative 1. 6, 5, 4, 3, 2, 1. 6, 5, 4, 3, 2, 1, 0. Formal charges. 6, 5, 4, 3, 2, 1, 0. What is this? 6, 5, 4, 3, 2, 1, 0. Negative 1 here. Oh, well, duh, look what I said. I could count them up if I want to, but this isn't even allowed because it's too many valence electrons. Yeah. So that's a bad structure based on what the O3. 20 electrons would be 2 more than the 6 and 6 and 6 of the O3 ozone. So what do you think? I would have to say this one looks just like this one. So based on formal charge, I don't know if there is a preference. Doesn't seem to be. I'd have to argue on other grounds, I suppose. Based on the fact that oxygen probably can't expand its octet anyway. It's not in the third period with unused d orbitals. I'm going to say this one's kind of silly. Have another example? There's a better example. Here's the thiocyanate ion with associated electronegativities of sulfur, carbon, and nitrogen. What's the possible What possible Lewis structure gives the best formal charge? I drew one with two double bonds between each carbon, sulfur, carbon, nitrogen, one with triple bond here, one with triple bond here, single on the other side. You see, I counted the formal charges. By now, you're sick and tired of that, so I won't do it again. But trust me, 0, 0, 1, 0, 0, 1, plus 1, negative 2. Oh my goodness. The negative 2 straight away kind of hints to me that this one's not favored. These look equivalent, 0, 0, negative 1, 0, 0, negative 1. But which one's more electronegative, nitrogen or sulfur? And we check out this out. Oh yeah, it looks like nitrogen's a little bit more electronegative than sulfur. So I would have to say that this one is a little bit more favored than this one. Oops, this one more favored than this one because of the electronegativity of nitrogen. I think I wrote that out here. Did I? I did. What do you know? Well, very favorable. Low % not very favorable, and almost none because of the negative 2 formal charge there. Was that the shortest video? Probably not. I tried. See you in class. Thanks guys for watching.